Class 10th Real Numbers Chapter 1 presented by E-Maths class Fatima Convent High School, myself Dipali. Moving further with this chapter, the next topic we are going to do in this lecture is revisiting irrational numbers. Now we all have studied about rational numbers and irrational numbers in class 10. We all know that the numbers which can be written in P upon Q form are called as rational numbers. And the numbers which cannot be represented in the form of P upon Q are called as irrational numbers. So, a number S is called irrational if it cannot be written in the form P upon Q where P and Q are integers and Q is not equal to 0. Some examples of irrational numbers are root 2, root 3, root 5. In general, root P is irrational where P is a prime number. Other examples are pi minus root 2 by 3, 0.101101101110, etc. Now in this topic, we are going to study and prove that root 2 is irrational number. To prove that, we need to understand one important theorem which is based on fundamental theorem of arithmetic. Theorem 1.3. Let us understand this. Let P be a prime number. If P divides A squared, then P divides A, where A is a positive integer. Let the prime factorization of A be as follows. A is equal to P1, P2 till Pn, where P1, P2 till Pn are primes, not necessarily distinct. Therefore, A square is equal to P1, P2 till Pn into P1, P2 till Pn, which is equal to P1 square into P2 square into Pn square. Now we are given that P divides A square. Therefore, for the fundamental theorem of arithmetic, it follows that P is one of the prime factor of A square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factor of A squares are P1, P2 till Pn, and so P is one of P1, P2, Pn. Now since A is P1, P2 till Pn, P divides A. We are now ready to give the proof of root 2 is irrational. Before that, let us understand this theorem with an example. A note to be taken into consideration. When I write 2/6, it means 2 by 6 or 2 divided by 6, that is 1 by 3. And when I write 2/16, it means 16 by 2, it is 8. So do you understand the difference between the two symbols? 2/A means 2 is divided by A, and 2/A means 2 divides A, or A is divided by 2. So be careful while writing this symbol. Now take example 6 is equal to 2 into 3. 2 divides 6 because 2 is a prime factor of 6, and 3 divides 6 because 3 is the prime factor of 6. If I square this number 6 and its prime factors, I will get 6a square is equal to 2 into 3 square. That is 36 square is equal to 2 square into 3 square. So 2 divides 36 and 3 divides 36 as well. So if we compare it with our theorem, let A be any number and its prime factors are P1, P2 till Pn. Then P divides A, or P1 divides A, P2 divides A. If I square this on both the sides, I will get a square is equal to p1, p2 till pn square. That is, a square is equal to p1 square, p2 square till pn square. This means that p is the factor of a square. So p1 will divide a square and p2 will divide a square. So our statement is easily understood that let p be a prime number if p divides a square, then p divides a, where a is a positive integer. Now let us use this to prove root 2 is irrational. This proving method is called proof by contradiction, as we are going to suppose it of the opposite what we require to prove. Let us understand it. Let us assume to a contrary that root 2 is rational. So we can find integers r and s not equal to 0 such that root 2 is r upon s. Suppose r and s have a common factor other than 1. Then we divide by the common factor to get root 2 is equal to a upon b, where a and b are co-primes. So b under root 2 is equal to a. Squaring on both the sides and rearranging, we get 2b square is equal to a square. Therefore 2 divides a square. But according to theorem 1.3, if 2 divides a square, 2 should divide a. So a will have two factors, 2 and any other number c. Substituting a, we get 2b square is equal to 4c square. That is, b square is equal to 2c square. It means that 2 divides b square and so 2 divides b. Therefore, a and b have at least 2 as a common factor. But this contradicts the fact that a and b have no common factor other than 1. This contradiction has arisen because of our incorrect assumption that root 2 is rational. Now let us understand this in a simpler way. Before that, one more note to be taken into consideration. If I have any rational number of the form a upon b, then property of a rational number is a upon b will have HCF is equal to 1. That is, HCF of A and B will be equal to 1 if A upon B is rational number. Now, to prove root 2 is irrational, we will suppose root 2 is rational. If root 2 is rational, I can write root 2 is equal to r upon s. Now, in case r and s has a common factor, we eliminate the common factor of r and s, then we get 2 is equal to a upon b. Now, we can write this as b root 2 is equal to a, that is, a is equal to b root 2, which shows that if I square this number on both the sides, that is a square is equal to b root 2 square, I get a square is equal to 2b square. Now this means that 2 divides a. Now if 2 divides a square, according to theorem, according to theorem 1.3, 2 has to divide a as well. That is, a will be some number 2 into c. If I square this on both the sides, I will get 4c square. Now according to result 1, a is equal to 2b square and a square is equal to 4c square. So can I say from result 1 and 2, 2b square is equal to 4c square. So b square is equal to 2c square. This means 2 divides b square and 2 divides b. According to theorem 1.3. Now if 2 divides b and 2 divides a, this shows 2 divides a as well as 2 divides b. But a and b can have HCF is equal to 1. Therefore, 2 cannot be the factor of A and B. Therefore, our supposition that root 2 is A upon B, a rational number, is wrong. Now, if a number is not a rational number, therefore root 2 is irrational. I hope this is clear to you. Let us take one more example related to this. Say root 3. Now if I want to prove root 3 as irrational, I will suppose root 3 let root 3 is equal to rational. Now if root 3 is rational, therefore root 3 is equal to A upon B. Therefore B root 3 is equal to A. Squaring on both the sides, A is equal to 3B square. That is 3 divides A square. Therefore 3 divides A according to theorem 1.3. Now if I have A divides, then therefore A will be 3c. Squaring on both the sides 9c square. Now according to result 1 and result 2, I have 3b square is equal to 9c square. So b is equal to 3c square. Therefore 3 divides b square and 3 divides b. Therefore 3 is a factor of b as well. Therefore, but HCF of A and B is equal to 1. Therefore, root 3 is not equal to a rational number. Therefore, root 3 is not rational. Therefore, root 3 is irrational. Now let us take example for a complex number, say 5 minus root 3. We have to prove this is irrational. Now let us say again root 3 is equal to a upon b. So I can write it as 5 minus a upon b is equal to root 3. So b5 minus a, 5b minus a upon b is root 3. But we already proved but root 3 is irrational. Therefore, 5b minus a upon b is irrational. Therefore, 5 minus root 3 is irrational. I hope this concept is clear to you. You will be able to solve exercise 1.3 easily now using these two theorems. Doubts are welcomed in the comment section. Next, we will be revisiting rational numbers and their decimal expansion. Thank you.